Okay, welcome to homework #2. Unfortunately, I haven't got the software yet, which has the title page, which tells you it is homework #2, where the topics are indices, error intervals, and bounds. Okay, so I'll go through all of the questions like on the previous video, and you can mark your work and correct things as you need to. Okay, right, let's begin with question 1. And let's see what the question says. So you've got here our two calculations, A and B, which you can see here. Use approximations. Now that's the key word here. Now if you approximate something at GCSE Maths, unless stated otherwise, you round to one significant, significant figure, which is really important, okay? So using this fact here, that's what approximation means. Show that the answer to A, this one here, is less than B. Okay, so 1.92 rounded to one significant figure. Well, the first significant figure is 1. The 9 rounds the 1 up to a 2. So that's going to go to, for A, first of all, it's going to be 2 to the power of 7 plus 6.9 to the 3. Well, 6 will go up to 7 from that 9. So it's going to be adding on 7 cubed. Now you're just going to go and work this out numerically. 2 to the 7 is 2 times by itself 7 times, which gives you 128, I believe, 128. And 7 cubed gives you 343. So 128 add 343. And that is going to give you, let's quickly work it out, 128 add 343, just making sure we're not making any mistakes here. 11, 7, 4. So 471 for A. And hopefully that's going to be less than the answer to B. Now 5 is already, you can't round that any better, that's already an integer. So for B, the 5 is going to just keep how it is. So it's going to be 5 multiplied by then this number here to one significant figure. Okay, well this is going to go to just, how many zeros got? 1, 2, just a million, isn't it? So it's going to be cube rooting a million. Okay, 1, 2, 3, 4, 5, 6. Now what number times by itself 3 times is a million? It is 100, because of course 100 multiplied by 100 multiplied by 100. Okay, you can see here you've got 1, 2, 3, 4, 5, 6 zeros. So that's going to go to 5 multiplied by 100, which gives you 500. And therefore you can clearly see that 471 is less than 500. Okay, so we're saying that it is true, number A is less than B. And let's look at the mark scheme. Yeah, perfect. Okay, so this is question 1. Done. Question 2, we've got this. Work out the value of 8 squared times by 8. And now what I would go and do here is, this is a laws of indices question. There's a 1 by the 8 that you just can't see. Okay, I'm going to write it a little bit clearer. 8 to the power of 1. And we are dividing by 8 to 9 divided by 8 to 5. Now just to quickly recap in case we've forgotten, our laws of indices. If you're multiplying indices with the same base number, which you've got here, okay, so if you've got, let's go and say, a number A to a power, and you multiply it by the same base number A to another power, you add the powers. So you go and take M and you add N. And with division, which you've got over here, similar sort of reasoning. Okay, if we've got a number A to the power of M and you divide it by the same base number to a different power, this time you take away the powers. Okay, so if we know that, so these are just our first 2 laws of indices. If we look at the first part here, okay, well, timesing with the same base, we just add the powers. So 2 plus 1 will give you 8 to the power of 3 in the first bracket, and we're dividing by in the second bracket, and we're taking away the powers there. 8 take away 5, which is 4. So 8 to the power of 4. Okay. Now, if you're dividing, which you are here, again, the same base number, 8 and 8, we take away the powers. So this is going to go to 8 to the power of 3, take away 4, writing out in full, which will give you 8 to the power of minus 1. Now, okay, you would have got 2 marks for this, but it says write the answer as a decimal. It's quite a nice question, this one, actually. Write it as a decimal. Now, this is actually another law of indices, which is the negative power law, which is to know if you've got a number A raised to a negative power, you take the reciprocal, which means you go 1 over your number to that power. Okay, so that's another law of indices. So this is just saying that in this case, because you can see you've got a negative power, you go 1 over your number, which is 8, and you put it to the power that is given, which is 1. So just 8 to 1 or just 8, they mean the same thing. Now, what is 1 over 8 as a decimal? Now, you might just know that it is equal to 0.125, and that's going to be the answer, 0.1225, which is your answer, okay? Now, if you couldn't remember that and you wanted to work it out, well, a fraction is a division, isn't it? So 1 over 8 means 1 divided by 8. So how many 8s go into 1, which of course it won't fit. So you can go and add in a few zeros over here and say, well, how many 8s go into 1? Well, 0, and you can bring up the point and carry the 1. 8 into 10 goes 1 time, remainder 2. 8 into 20, okay, 8 into 20 goes twice to 16, remainder 4. And then 8 into 40 goes exactly 5 times, which is where this over here comes from. Okay, very nice. Question 3. Question 3 is another approximation question. So again, using approximations, that's the key word here. Let's just highlight that. Again, just to make it really clear, that means we're going to round to 1 significant figure. So root 97, of course, if you try to do that, you're going to get a horrible decimal. Now, you're going to probably recognise that's going to be 100, and it is 100 because one significant figure is 9. The 7 rounds up to 100, so we're doing the square root of 100 plus, then this number here, the first significant figure is 2. The 0 rounded down to 2, so just plus 2 to the power of 3. And we are dividing by 0.49, where your first significant figure is to 4. The 9 rounds to 4 up to 5. So over 0.5. Okay. Now if we look at the numerator here, well, root 100 gives you 10. 2 cubed, 2 times 2 times 2 gives you 8. So 10 plus 8. And we are dividing by a half. So we've got 18 divided by half. And if you divide by a half, your number is going to double in size because a half goes into 18 36 times. So the answer should be 36. Let's check the mark scheme. 36 is looking good. So perfect. 36 can go in there. There we go. Okay, question 4 is a nice one. Laws of indices. Okay, so simplify this, giving your answer as a power of 2. Now that's a really key part of the question. That means the answer must have a 2 in there. Now, these are both powers of 2, 2 to 6 and 2 to 4, but 8 isn't. So I want you to recognise that 8 can be written as a power of 2 as 2 to the 3. 2 times 2 times 2 gives you 8. So I can now rewrite this as the following. 2 to the 3 times 2 to the 6 times 2 to the 4. And we've just seen it previously. If you're multiplying indices with the same base, okay, this is our general rule, you add the powers together. Okay, so this one's going to go to 2 to the power of 3 plus 6 plus 4, showing the exam that all of our working, which will give you 2 to the power of 13, 2 to 13. And this should be the answer. Check the mark scheme. Good. So this is my answer as a single power of 2, 2 to the 13. Right, question 5 is a more tricky question. I would say this is probably grade 7, 8 question on bounds. Okay, and we've got this equation here. It says P is equal to 68.3 correct to 1 dp. Now when you see this kind of question, right, when numbers have been rounded to to something, it is, well, straight away think about error intervals and getting down your error interval for that number. So if I go and do that for this number, now if you're in year 11, this is content from last year, so just to recap quickly, the way that I would do this is draw out a number line and put our number in the middle, which is 68.3. And because we're rounding to 1 dp, which is this point here, you want to go one above and one below 68.3, so 68.4 and 68.2. You then want to go in between these two numbers to get your upper and your lower bound. So that's going to go 68.35. That's going to be 68.25. So what you're saying is, for P, I'm going to write it down here for some room, 68.3 must be bigger than or equal to 68, and use this number, 0.25, less than 68.35. So just to make sure it makes sense, what this is saying is this is the smallest possible value, and you call it the lower bound, that to one decimal place rounds to this. Check it makes sense. Well, the 5 rounds a 2 up to a 3. It does make sense. Anything smaller, like 68.24, would round down to 68.2. So that is definitely my lower bound. Now the upper bound, it says 68.35, which if you round it to 1 dp, would give you 68.4, which isn't this number, but this inequality sign means you don't include this number. You go just below it. So you would just go to 68.349. But doing calculations with this number would be an absolute pain. So you just use 68.35 and use this inequality to say you don't include this number, you go just below it. Okay. Now let's do something very similar with B. We've got 8.7 again to 1 dp, so something similar here. Again, let's put our number in the middle. So we've got 8.7. We're a little bit cramped, but it'll be fine. 8.7. We can go one above, one below again to 1 dp to 8.8 and 8.6, and we can go in between these two values here to get our upper and lower bounds, which are going to be 8.65 and 8.75. So the error interval for this number, 8.7, is going to be the following. So you want your lower and your upper bound of 8.65 and 8.75. And always should check it makes sense. Is that the smallest number that to 1 dp would go to 8.7? It is. Anything smaller would round down. And that is the biggest number. You don't include it, you go just below it. Okay, that would round down to 8.7. Perfect. Good. So straight away you've got marks just for writing down the error intervals. Now to work out the lower value for m, this thing here, you've got to think quite craftily here. This will catch a lot of people. This will catch a lot of people out. So you want to get the m, and you want to get the lower bound. So let's just call it the minimum, or you could call it lower, the smallest value. Now to make a fraction the smallest it can possibly be, you want the numerator. Okay, you want the numerator to be the minimum it can be, and the denominator to be the maximum it can be. And if that doesn't make sense, let's think of an example. If we have this 10 divided by 2, of course that gives you 5. If you want to make this value as small as it can be, you want the top number to be smaller. So let's just go and say it was 1, and the bottom number to be bigger. Let's go for 20. Okay. Now, 1 divided by 20 would give you a really small decimal, wouldn't it? Okay, so that would be much smaller than the number 5. Whereas if you did the opposite thing and you made the top bigger, let's go and say 100, and you made the bottom smaller, like 0.2, okay, well that would go to 500. Your answer would get far bigger. Okay, your answer would get far bigger. So to get the smallest possible answer, you want the minimum value on the numerator and the maximum bottom. Now the thing is here, the 2's fixed. So all I've got to concentrate on is this numerator. I've got to make this the smallest it can possibly be. Now to make p minus 2b the smallest it can be, I've actually got to go and then think about, right, I've got to get p to be the smallest value, okay, and b to be the maximum value. Because now if you think about it, if you go and take away, if we go and look at a number like, I don't know, 10, take away 2, if you make the first number smaller, let's go and say, I don't know, 8, and the second number bigger, okay, like, well, that's just not a regular example, but just to make this the smallest it can be, the minimum, the p's got to be the smallest value, so I'm going to call it p minimum, and the b has got to be the biggest it can possibly be, and that will give me the smallest numerator. I'm just going to be dividing that by 2. Okay, now p minimum, p is the first number. I'm going to be wanting to use the lower bound, 68.25 over here, and for b maximum, b is this number 8.7. I want the maximum value, so this 8.75. Okay, so I want this number over here. So I want this one for p and this one for b. Let's make it a little bit clearer that this is for p and this is for b. And then it's just a case of putting my numbers into my equation. So M minimum is going to be equal to P minimum, which is 68.25. Take away 2 lots of B max, which is 8.75, and I want to then divide by 2. Okay. And then if I put this into my calculator, which I'll get on the screen, let's see what that gives us. Okay, so just being careful now with my typing in. So 68.25, take away 2 lots of 8.75 over 2. No mistakes there, typing it all in. Okay, and I get this 208 over 3. Just looking at the mark scheme, hopefully there's no mistakes there. Okay, which as a decimal gives us 25.375. Okay, which is correct. So 25.375. 25.375. And this is the answer. Okay, this is quite a tricky question. That's like grade 7, 8. Okay, but hopefully the thinking there made sense. If it didn't, of course, you can comment below, and you've got intervention. Good. Moving on. Question 6 is another kind of question that's similar. It's still probably grade 6, 7, but a little bit easier this one because there's just less going on. But you've got 2 numbers, A and B. This time, they're rounded to significant figures. Okay, but again, as soon as you see a number rounded to something, you're thinking error intervals. Now, in this case, your third significant figure is the 1, 2, 3, is that 2, which is in the 100ths column. What I'm going to go and do is always get the error intervals done. So my number is 4.72, and the third significant figure is that 2. So you go 1 above it to 4.73, and 1 below it to 4.71, and you go in between these 2 values to get the upper and the lower bound. So lower is going to be 4.715, upper is going to be 4.725. And do the same thing for the next one. It's going to do it in blue. Okay, so again, number in the middle, which is 158 to 3 significant figures. Well, the third significant figure here is 8, which is in the ones column, units. So you go 1 above and 1 below, you go up to 159, you go down to 157, and of course you go in between again. So we go to 157.5 and 158.5. Now, you want to work out the upper bound of A divided by B. So you want the biggest possible value. You want the biggest, because upper bound is like the maximum value. Okay, you could call it upper, I call it max, that's fine. Now to get this fraction to be as big as it can be, you want A to be the biggest it can be. Okay. Sorry, what am I saying? That's bad notation. It says work out the upper bound of A divided by B. Let's just go and call it the maximum value. Okay, I wrote max A, doesn't make sense. To make this fraction as big as it can be, right, you want to make the numerator the maximum it can be and the denominator to be as small as it can be, for the same reasoning as before. So I want, if that's A and this is B, right, I want the biggest value, the upper bound for A, and the smallest for B. That will make my fraction the biggest it can possibly be. Okay. Again, if you want to think about it, like 10 divided by 2, if I make the top bigger, like 100, and the bottom smaller, like 0.2, the answer will go up. Okay, so this is going to be 4.725 divided by 157.5, okay, which will give me a little decimal. That's fine. Let's see what it gives us. So 4.725 over 157.5, which gives us 0.03. I'm going to check the mark scheme. 6, there we go, 0.03, that is correct. So 0.03, this is your answer. Okay, good. Question 7, another bounds question. Okay, there we go. Oh, I don't want that there. Let's undo that, and let's zoom up a little bit. Right, this one is the following. To be rented, a bedroom must have a floor area of at least 6.51 meters squared. Okay, so probably looking at a rectangle. Yeah, there you go. It's got a rectangular floor. Perfect. The floor measures 2 by 4 by 2.9. Each correct to two significant figures. So again, right, straight away, you're seeing rounding here. Now for the first number, and write out your error interval. So before I even read the question, I'm not even interested in that. I want to get these numbers down as error intervals. So let's go and do that. Number line for 2.4. So this is for our number 2.4. So 2.4 in the middle. Now your second significant figure is the 4. So the tenths column. So you want to go one above, one below that tenth, that 4, to 2.5, and then to 2.3. Okay, and you go in between those two values to get our upper and lower bound. So 2.45 and then 2.35. And do the same sort of thing for the second number, which is 2.9. So 2.9 in the middle. Again, second significant figure is this 9, which is the tenths column. So you go one above, which will take you to 3, one below, which will be 2.8, and you want to go in between these two values here, which will give you 2.85 and then 2.95, and there we go. So I've written my error intervals out straight away. And it says, show that the bedroom, it can be rented. So to be rented, a bedroom must have a floor of this here. Okay, so it must have at least, so you want to say, you're saying that even if you had the two smallest dimensions, it would still be at least this. So you've got to think, right, do I want the upper bounds or the lower bounds or upper bounds? If it's got to be at least this, you want to prove that even with the lower bounds for each of these here, hopefully, that's still going to be bigger than 6.51. Okay, if I've understood the question, which I think I have, so it should be fine. So that should be a rectangle. So even if this is, the width is 2.35 and the height of it is 2.85, hopefully that's still going to be bigger than 6.51. Let's double check that. So 2.85 multiplied by 2.35. Let's see what that's equal to using our calculator. Okay, so let's have a look. 2.85 multiplied by 2.35 gives me 6.69, which is bigger, isn't it? So that should be absolutely fine. So look at the mark scheme. 2.35. That should be fine. Just checking. Sorry, I'm checking the mark scheme. That should be absolutely fine. 6.698. Yeah, perfect. Good. Yeah. So I'll just check I get the right numbers here. So that is correct, because this gives you 6.6975, which is bigger than 6.51. Okay, even with the two smallest values for the width and the height, you get a floor bigger than 6.51. So that is all correct. Fantastic. Good. Let's move on to our next question. Okay, another sort of similar bounds one. These ones, they're not, they take a bit of thinking. They're not always that easy. But if you just begin with the error intervals, you'll be good to go. So when I see this question again, I see a number to the nearest one integer. I see a different number b to one significant figure. And it says work out the upper bound for this here. Now let's just go and again write out our numbers as their error intervals. So I've got 65 first of all. Okay, and this time to my nearest whole number, nearest one, you go one above, you go one below. So 66 and then 64 down here. And we can go in between. Get those two values to give you 65.5 and 64.5. That's for the number A. And then for B, let's go and do it in blue over here. For B, get out our number line again. There we go, which is the number 30. Okay, and 30 has been rounded to one significant figure, which is where the 3 is, and the 3 is in the tens column. So you want to go 10 above and 10 below your number 30, so to 40, and then down to 20, and we go in between these two numbers here to 25, and to 35. So the error interval for this one is going to be 65 bigger than or equal to 64.5 and less than 65.5. This one's going to be 30 bigger than or equal to 25 less than 35. Okay. Now to get this thing here to be the biggest it can possibly be, again, you want the first part to be the maximum it can be, take away B to be the smallest, right? For a subtraction, okay, for a subtraction, so let's go for A squared, take away B squared, it's still a subtraction, that's the key thing. To be the maximum it can possibly be, you want the first number to be as big as it can be and the second one to be as small as it can be. That will give you the biggest output. And you can try it with numbers just to prove it yourself. Okay, so for A, the max value is this one, and for B, the smallest one is this one. Okay, so I want this one, I want this one. Now putting it into my calculation, it's going to be 2 lots of A squared, because we've got 2A squared, take away B squared, where I'm using the biggest for A, 65.5 squared, take away the minimum of B, which is going to be 25 squared. And let's put that into the calculator, sorry. Let's see what we get. Refresh that. So we've got 2 lots of 65.5 squared. Take away 25 squared, which is 625. Let's just put it in just to be safe. 625 squared. And what does that give you? It gives you this, which gives you this. And let's check the mark scheme for any mistakes, but it should be good. Question 8. 7955.5, which is what I've got. Perfect. So that gives us this 7955.5, which is the answer. Good. Okay, moving on. Right, we've got this here. Again, it looks like another balance question. Jack is loading a van. The van can safely carry this much furniture. Okay, so it can safely carry that much furniture. Jack has already loaded 1,200 kilograms of furniture to nearest 50. So straight away, that's just going to write out the error interval for this number. Just getting it done straight away. So I've got 1,200 as my number in the middle. To the nearest 50 means I want to go 50 above and 50 below. That's what I'm rounding to. So 1 to 50 and then 150. And of course, in between, we can now go to 1175. And we can go to 1225. Just double check it makes sense. To the nearest 50, right, so write it all out. So 1,200 must be bigger than equal to 1175. And it must be less than 1225. Nearest 50, where would that go to? This, that's correct. Anything smaller, we go to 1150, so that's correct. 1,200, yeah, perfect, and that would also work. Good. A table has a mass of 140 to the nearest 10, so let's go now write out this error interval over here. So the table has got a mass of 140, okay, to the nearest 10, so you want to go 10 above, which is 150, and 10 below, 130, and let's go in between these values now, 2, 135, 135, and 145, so the error interval is going to be 140, bigger than or equal to 135, less than 145. And it's saying, can the table safely be loaded? Now, the thing is, if we're already at this here, right, now, if you're like looking at safety, you're always thinking, well, if you've got like the heaviest possible loads, would everything still work? So if the van's already had, let's just go and say the biggest load it could have, which is going to be the maximum, right, 1225, so the biggest possible value, and then you added on the table of the heaviest weight, which is going to be 145, is that still going to be below 1375? Now, if you add those together, that gives us, add the 5 on there, 1230, 133. Let's just use a calculator just to make sure it's going to be safe and good to go. If we add these together, okay, we're going to get 1225, add 145. What does that give us? 1370, which is fine. So even with the biggest possible loads, right, 1370 is less than that 1375, which means it's going to be safe. Yeah, because even with the heaviest furniture load and the heaviest table, like the maximum values, so the max load and the max table, it's still below what the van gets. So it should be safe. So if we look at the mark scheme, what question are we on? Question number 9. Yeah, perfect. That's perfect. That's all safe. So there we go. Now this one here is actually, question 10 is now much easier. We're actually kind of going backwards here. Okay, we're just literally writing error intervals now and doing nothing with it. So you've got a baby, it's 3.6 to 1 dp. Okay, now we've been going through quite a lot of these ones already, so let's just do this one quite quickly. 3.6 in the middle, to 1 dp we go one above, 3.7, one below, 3.5, and you go in between for your error interval numbers, which is going to be 3.55 and 3.65, so it's going to be your mass, which is 3.6. Okay, they've written it as the mass must be bigger than or equal to this, less than this one, which is this one here, isn't it? So, be careful with the inequality signs. You want this one. It's got to be bigger than or equal to and less than. Because, of course, if you included 3.65 to 1 dp, that would round to 3.7, which is not this. By having this inequality with no sting underneath it, it means you go really 3.64999. But, of course, writing this is an absolute pain, and using calculations with this would be an absolute pain. So you just use this number here. Good. Okay, I'm not quite sure how much more we've got left. 11. Right, I've got quite a few more questions left. Crikey. Let's keep going. This one here, number 11, what time is it? What time is it? Not going on too long. We'll keep going. Number 11, I've got x here. It's 15.8 when rounded to 3 sig figs. So the third significant figure here is, of course, the 8. Okay, so 1, 2, that 8 is the third sig fig, which is in the tenths column. So when you draw out your number line, which I'll do here, we've got 15.8 in the middle. And because it's in the tenths column, you want to go one above and one below that tenth to 15.9, and one below to 15.7. And then, of course, we go in between to get our upper and lower bound, which will be 15.75, halving it, and then 15.85. Again, making sure you want the right notation. So you're going to be wanting this one here, isn't it? 15.75 here, 85, good, with the correct notation. So this one, you include this number, you don't include 15.85. We've been through that, so that's going to move on from that one. Question 12. This looks like a more challenging question for sure. It's a indice question, probably at grade 8, I would say. Given this division here equals to 2 to 17, work out the value of x. Now, what you should really first do here is maybe rewrite this first part as 2 to the power of 3x divided by 2 to the power of x minus 5. Okay, now you know if you divide indices with the same base, you know that you can take away the powers. Okay, so it's just a more complicated application of that kind of question. So in this case, we can go and say, well, that's going to be equal to 2 to the power of 3x, and we're going to, let's go for small room actually, getting a bit cramped, so I'm going to write it below it. It's going to be 2 to the power of 3x, and I want to take away all of this power over here. So be careful to put it into brackets, x minus 5. And that's going to go to, so 2 to the power of 3x. Now you've got to really distribute out this negative to everything in the bracket. So minus x, and that will go to plus 5. You've got the timesing of two negatives. So minus x plus 5, which will go to 2. 3x minus 1x is 2x. So 2x, and I've got the plus 5 there. Now you know, so this here, this part here is the same thing as this. So we've got 2 to the power of 2x plus 5 must be equal to the right-hand side, which is 2 to the power of 17. Now, because these two things here, they've got the same base number and they're equal, it must be true. For these things to be equal, the powers must be equal. Yeah? So 2x plus 5 must be equal to 17. It needs to be the same. That has to be the case. So I can go and write the, running a room bit, that 2x plus 5 must be equal to 17. Now solving this equation, let's go and take away the 5 over here to give us 2x being equal to 12 and divide by 2 to give us 6. So x must be equal to 6 for number 12. Okay, and that is correct. Perfect. Good. Number 13, we're getting there. A wall has been rounded to 9 meters to the nearest meter. So to the nearest 1. Write down the error interval for the length of the wall. So this one's, again, just a simple error interval question. Number line. Number 9 goes in the middle. Nearest meter, 1, 1 above, 1 below. And then we go in between these two numbers, okay, to give us 9.5 and 8.5. And then you just write these numbers here. So 8. Oh, that's fine. Sorry, 8.5, 9.5. So I thought they wrote. No, don't worry. That's fine. The length is bigger than or equal to 8.5, less than 9.5. That's just a standard question on error intervals. Let's just double check it. Question 13 is looking good. 8.5, 9.5, perfect. All good. All good. Okay. Next question. Let's have a look. We've got this. Work out the value of 81 to the power of negative 1 over 4. Now, another law of indices, more of a grade 6 one, this one, is if you have a number raised to a negative power, where the numerator is 1 and the denominator is a number, well, the negative power always means reciprocal, 1 over. If you see a fractional power, you root your number, a, and the root that you take is the denominator of the fraction, which is n, which can go here. So this is our general rule. So I'm seeing negative power, I go 1 over my number 81. I root that number to the denominator of the fraction, which is 4. So I want the 4th root of 81, which is 3, because 3 times 3 is 9, times 3 is 27, times 3 is 81. So my answer is a third, or 0.3 recurring, but that is fine. That is my answer. Good. Okay, part B is looking like a nice one. Write this up here as a power of 2 in terms of x. Now you can see here that 16 and 8, these are currently not written as powers of 2. Let's go and do that. 16 is the same thing as 2 to the 4, and 8 is the same thing as 2 to the 3. So this first part is 2 to the 4 multiplied by 8. I'm just going to put it in a bracket, which is 2 to the 3. And now I've replaced this 8, okay, that 8 with 2 to the 3, and the power is still there. Okay, it's still going to be 2 to the x. Okay, so I've just replaced the 8 with 2 cubed and 16 with 2 to the 4. This here is a law of indices within itself. If you've got a base number raised to a power raised to another power, you simply multiply the two powers together. Okay, it's your power law. So this will go to 2 to the 4 multiplied by times those together. 3 times 2x gives you 6x. There we go. And then, of course, this down here is your multiplication law of indices. You're timesing with the same base numbers. You add the powers together. So it's going to be equal to 2 to the power of 4 plus 6x, which you can't simplify because they're not like terms. So you can just go and write it as that, 4 plus 6x. And this is your answer. Okay. 15, which question is that on? Sorry, 14b. Perfect, we're looking good. Question 15 is to find two sets of values for c and d such that 16 to the power of c is equal to 2 to the power of d. That's an interesting question. Let's have a look. Okay, what I'm thinking here is, right, 16 is equal to 2 to the 4. So if I write 16 as 2 to the 4 to the power of c being equal to 2 to the power of d. Now, using laws of indices here, power law, what we just saw up here, I can rewrite this just simply as 2 to the 4c being equal to 2 to the power of d. So this is saying, if we look at for these to be equal, they've got the same base number. Okay, well, if we look at the exponents, 4c must be equal to 2d. Let's just go and write that out. So, or d is, let's go and write it in blue. So d must be equal to 4 lots of c. Okay, so whatever c is, d is 4 times it. Okay, so let's just go and check this. Let's just go and say, I don't know, if c was equal to 1, if c was equal to 1, d would be equal to 4 times 1, which would be 4. So if c was 1 there, d would be 4. Does that make sense? Let's double check. 16 is the power of c, which is just 1, is equal to 2 to the 4. Yeah, that makes sense because 2 to the 4 gives you also 16. Let's use another one. If c, just choose a value because you can choose any value. If c was equal to 2, what would d be equal to? D would be 4 times that c value. So 4 times 2 would give you 8. Does that make sense? Let's double check it. So we're saying if c was 2, d would be equal to 8. So 16 to the power of c, and c there is 2. Okay, that'll give you 196. And then 2 to the d, which is 8. Yeah, they would both give you 196. Okay, for sure. Would they? Double check. 2 to the power of 8. 2 to the power of 8 gives you... Oh, sorry, 16 squared is what we're doing. It's 256. It's really silly. That's really silly, sorry. That gives you... It works, they give you 256. So basically, right, as long as that's satisfied, right, as long as your d value is 4 times the c value, you can have whatever you want to. Okay, so you might go and choose d to be 3, so c would be equal to 4 times that, 12. Okay, there we go. Good question, that one. Really good question. Oh, I've got another question below. 16, this one is really easy one. Laws of indices, we are dividing. This means we've got 3 to the 12 divided by 3 to the 7. Again, if you divide with the same base numbers, okay, in this case the base number is 3, we take away the powers. That's your general rule. And I'm writing out every single time just to keep refreshing it in our minds. Okay, it's always a good thing to do. That's going to go to 3 to 12 take away, what am I doing? 12 take away 7, which gives you 3 to the 5. And that's that one. Okay, so 16 is 3 to the 5. Oh, as a whole number. Right, could be careful. Give your answer as a whole number. So 3 to the 5 is 3 times 3, which is 9. 27, 81 times by 3 again. Gives you 243, doesn't it? 243. That's correct. 243. Okay, just double check. I've done my time is incorrect. Calculator. 3 to the power of 5 gives me 243. Perfect. Good stuff. Okay, number 17. This one here, we're getting close to the end. 17. Yeah, last question. Good. Okay, ratio one. A nice question to finish up with. We've got write this here in the form n to 1. Again, this is recognising you've got laws of indices here. Okay, the first part, again, you're timesing with the same base. I'm going to go and add the powers. So 6 to 5 gives you 11. So you've got 3 to the 11 to the other one, 3 to the 7. Now, to get the second number to become a 1, you want to divide. So for that to become 1, you want to divide 3 to the 7 by itself, because anything divided by itself will give you 1, which means you do the same thing over here. You divide by 3 to the 7. So that's good. On the right, that will give you 1. And then, of course, 3 to the 11 divided by 3 to the 7. You're dividing. You take away the powers, laws of indices. That will give you 3 to the power of 4. So 3 to the 4. Okay, where n is an integer, so as a whole number, not as a indice. 3 to the 4 is 3 times 3, 9, 27, 81. So it's going to be 81, 2 to 1. And that should be it. 81 to 1. There we go. Perfect. 81 is my answer for this one. And I believe that is it. Okay, that is the mark scheme. Okay, thank you for watching. Of course, any questions, you can comment in the comment section below, and you've always got the interventions to come to for any questions. Keep up the good work, and hopefully that was useful. Thank you.